Thank you, Joris. So indeed, I will show you today some of our first 2D numerical wind models of the Wolf Rayet outflows. And I will not only show you some 2D models, but I will also try and show you some, or I will also show you some of our first 3D models that we've developed in our group. So let's begin by talking about why we are interested in Wolf Rayet stars, and then we'll explain why we need these higher dimensional models, right? So what you see here is a possible schematic life cycle of a very massive star. So massive stars, such as all stars, are born when a gas cloud collapses. Then the star goes on to the main sequence where it spends, the star is born and goes to the main sequence where it spends most of its life. And then if your star is massive enough, as in above 30 solar masses or something, it will first undergo a luminous blue variable phase, where it will expand most of its outer envelope, and then it will become a Wolf Rayet star. And the Wolf Rayet phase of the star is the last phase in the star's life before it goes supernova and it becomes a black hole. And during this Wolf Rayet phase, the star will also have a significant mass loss that can affect the mass of the remnant black hole. So if you want to understand the plot here, and this is a plot that displays the mass distributions of all the black holes that are found by LIGO and other sources. So if you want to be able to explain the mass distribution of black holes that we see here, we need to very well understand the life cycle and especially the Wolf Rayet stages of stars. So let's have a look at a Wolf Rayet star on the HR diagram. So Wolf Rayet stars stars are born on the main sequence, and then they will live their main sequence life, and then they will lose their outer envelope. And in the previous plot that I showed, this happens through an LBV phase. But if the stars are a little less massive, this can also happen in the red supergiant phase, or additionally, this could also happen due to binary stripping. So the formation method is not per se known, but there, we know that there has to be some sort of moment in the star's life where it's stripped from the outer envelope. And then the star will go to the left side of the left hot side of the HR diagram and be a Wolf Rayet star for a while. And these envelope stripped Wolf Rayet stars typically are left with a solar mass, with a stellar mass of about 10 to 25 solar masses, and a luminosity between 10 to the 5 and 10 to the 6 times the luminosity of our sun. Now, when we want to describe the radius of Wolf Rayet stars, that's a bit more complicated. Typically, for a single Wolf Rayet star, you can find in the literature many different numbers for the radius. So here I took an example for WR134, where if you try to derive its radius from observations, you typically find something like 10 solar radii star. And if you take a slightly more complicated model, you can bring this down to 2 solar radii. But when you try to evolve this star or this type of star with an evolutionary model, you would typically end up with a 1 solar radii Wolf Rayet star. So there's a lot of uncertainty here, and this is what we call the core radius problem, and I'll get back to that a little later. And additionally, a similar problem arises when you look at the temperature, and this is of course related. If you have the same luminosity but a bigger star, you will find you will derive smaller, lower temperatures from spectral information. So in this HR diagram, a couple of Wolf Rayet stars are plotted, and in the black dotted line central in the figure, this is where the helium 0H main sequence line is. So from evolutionary models, we would expect that the stars, that the Wolf Rayet stars are on the left of this line or on top of the line. But when we measure or when we observe our Wolf Rayet stars and we take very simple first 1D models, we see that all the stars actually lie on the right of this model, of this helium ZAMS. And we have a partial explanation for this, and that has to do with the morphology of a Wolf Rayet star. So a Wolf Rayet star, which is found in a very thick optical wind, And unlike solar star or O-type stars who have their photosphere very close to the hydrostatic surface of the star and then are then covered with an optically thin wind, Wolf-Rayet stars have this very dynamic optically thick wind. And due to the thickness of this wind, the actual photosphere, so which I've indicated here on the right drawing with the red dotted line, is actually a couple times the Wolf-Rayet stellar radius away from the actual stellar surface. So this wind is driven by radiation, and there's a lot of radiation-driven convection going on, so a lot of motion going on in this wind as well. Yeah. So the fact that the photosphere is so far out in the wind means that if we observe the star, we actually collect with our telescopes light that comes from the photosphere and not light that comes from the hydrostatic stellar core. So in the study of Wolf-Rayet star, there's a couple of open questions that we still want to answer. And so one of the things that we want to understand and be able to model is this stellar wind and the structure formation that goes on in stellar winds. And if we understand that structure, we can start to understand how this structure affects the observations that we make in the construction of spectral lines in our spectra. And if we know this, we can understand the core radius problem better, and we can explain the difference between the observed and inferred temperatures of the Wolf-Rayet star as well. So when we want to learn something about a particular star, so for example, Wolf-Rayet star here is what we do. We typically point our telescope at it. So here on the left, you see a nice pretty image of a nebula surrounding Wolf-Rayet star. So we point our telescope at it typically, and then we retrieve a stellar spectrum. And for Wolf-Rayet stars, these spectra typically have these very clear emission lines, as you can see in the figure on the top right. And then we can fit these spectra using spectral fitting codes. And when we do this, we can from the fitting infer stellar parameters such as the stellar radius, the stellar mass, abundances, and so on. However, to do this spectral fitting, we need to assume some sort of model atmosphere for the star. So, of course, because your star is covered in a lot of gas of the wind, this wind gas will affect the spectra, or the spectrum that you get out of the star. So what we typically do when we do this spectral synthesis or the spectral fitting is that we assume that the wind surrounding the star is described by this beta law. And the beta law is an analytic expression to express the velocity field of a wind outside of a star. So I've plotted the beta law here. So as a function of radius, we can analytically say how high the radial velocity of the wind is here on the plot on the right. And if we have a velocity profile and a mass loss rate, we can also infer a density structure, and that allows us to then compute its effect on the synthetic spectral line that we generate from this. So beta law is very simple, but there's some minus points to it that it's first of all spherically symmetric, so, and it's also uniform. However, some codes can correct for clumping. We still don't have any real structure in these beta law winds. So these are the models that are typically used in codes such as Power and CMFGen and FastWind. And although these work very well for O stars, for Wolf-Rayet stars, we know that the winds are actually not described by a beta law. And this was shown recently as well by one of our collaborators, one of our group members, Luca Poniatowski, who showed that the actual winds of Wolf-Rayet stars form this velocity field that you see here on the right, which has these typical two lobes where your wind accelerates, as you can see from the dark black line, and then decelerates a bit, and then it re-accelerates again. And these are models that Luca computed using a new type of description for the opacity, to which I will come back later. And we call this a hybrid opacity description, where we combined basically line driving in the outer wind with the typical static opal opacities in the inner wind. However, these models are still 1D, so still spherically symmetric, and thus don't really account for any turbulence or convection in the winds. Our theory predicts that we should find convection and turbulence and structure formation in stellar winds of Wolf Rayet stars, at least. So to better understand the structure formation and how they affect the formation of spectral lines, we actually do need 2D models or even 3D models to fully model these winds. So yeah, I can now go to the numerical method. So here I will explain to how we plan on modeling these winds in a multi-D setup. And the method that we use is radiation hydrodynamics via the flux limited diffusion approach with line driving. So that's a whole lot of words. And what radiation hydrodynamics actually means is doing hydrodynamics, so doing the motion of gas combined with some sort of radiation prescription. And flux limited diffusion is just a particular flavor of doing radiation hydrodynamics. And then line driving, as I mentioned before, is taking into account the line opacities in the dynamics of the wind. So I will show you a couple of equations. So we'll go through the equation of radiation hydrodynamics in a very slow way. So here you see just the normal hydrodynamics equation that explain the conservation of mass on top in the continuity equation, the conservation of momentum in the middle equation, and then the conservation of gas energy in the bottom equation. So with these equations, we can, if we have an initial condition, if we have boundary conditions, we can predict how a gas field will evolve through time. And we want to combine this then with some sort of radiation description. So typically, if we want to describe radiation, we would do this via the radiative transfer equation. But radiative transfer equation is computationally very heavy to solve. So that's actually unfeasible in like large multi-D time-dependent simulations. So what we do instead is we take the radiative transfer equation, but we integrate it over frequency and over solid angle, so that we can work with the first, what we call the first moment equation of radiative transport. And so we also call it the radiation energy equation. And what this equation describes is the conservation of radiative energy. Yeah, so you can see that it has a similar shape to our gas equations. So the top three equations that describe the gas. And it's of course no coincidence that makes it nice and easy to combine both equations in one code. So the top three equations describe gas motion on their own. The bottom equation describes radiation or transport of radiation on its own. And what we now want to model as well is, of course, the interaction between the gas and the radiation. And we can do this by adding source terms to the right-hand side of the equations here. And so one of the main important interactions that we want to describe for stellar wind is, of course, radiation force. So the radiation force is when your radiation encounters gas, it transfers momentum from the radiation field to your gas field, or to so it adds momentum to your gas. And you see that the radiation force here has the same expression that you've probably seen before as well. So it's dependent on the density, local density, the gas opacity kappa, so the interaction constant between radiation and gas, and also on the radiation flux F. So if we add momentum to our gas system, that means that we also add kinetic energy to our gas system that we have to take into account and add in the gas energy equation. And when your radiation is actually accelerating your gas, that means that your radiation is providing a force or a work, and that means that energy should be leaving your radiation system as well. So that's also described here with this bottom work provided source term. Another interaction that we describe is the heating and cooling of gas. So when, for example, your gas gets shock heated, it will try and cool down by radiating away energy, and that's one of the effects that's described here with these heating and cooling source terms. And these heating and cooling source terms will also, well, they will depend on the gas temperature, on the radiation temperature, but also on the opacity. So again, this interaction constant between the gas and the radiation. And then finally, we also want to include gravity in our model, which is of course very important in wind models because the wind structure is set by the interaction between outward radiation force and inward gravitational force. So this is also incorporated in our momentum equation and gas energy equation. So we have now a description of the evolution of the gas field and the radiation field. There's one more term that we don't know, and that's what the radiation flux is. So that's present there in the bottom equation, the radiation energy density equation, but also in the radiation force and its kinetic term. And to estimate or to calculate the radiation flux, we use the flux limited diffusion approximation. And what we do in this approximation is basically say, okay, let's describe our radiation energy density as a diffusive field. And then we can say that the radiation flux depends on the local gradient of the radiation energy density, E. And then we put in a correction term for when we leave the diffusion regime and then go to a more free streaming regime. And we see then, okay, so we can express our radiation flux as the gradient of E times some constants in front. And again, this opacity is very important here. So flux limited diffusion is computationally very cheap. So this is a really nice way of doing radiation hydrodynamics where we describe our radiation field in a time-dependent manner. And that's important for our very dynamical simulations. However, a note to make here is, flux limited diffusion approximation is not fully exact. And by doing this first moment equation for the radiation, we lose spectral information of our radiation. So if we want to, in the end, after doing our simulations, retrieve spectral information or information on the frequency of the radiation, we'll have to do this via a post-processing method. So this flux limited diffusion radiation hydro approach has been implemented in the multidimensional MHD code MPI AMRVEC that has been developed or under development at the the mathematics department at KU Leuven. And implementation has been described in a recently submitted paper to ANA. So one last ingredient that we need for our models is a good description for the opacity. So as I've said before, this opacity is prevalent in the radiation force, so in the momentum balance, also in the heating and cooling terms, and thus sets the temperature structure of the wind. And it's also important in the flux limited diffusion closure relation, that is expression for the radiation flux. So this affects the transport of radiation through your wind. So a typical description of opacity that we use in astrophysics is often the Opal opacities. So these are tabulated Rosland mean opacities that depend on temperature and, well, on your chemical composition, but also on temperature and density. And we've noticed that if we try to drive a Wolf Rayet wind using only Opal opacities, there's not sufficient radiational force or not sufficient interaction between your radiation and your gas to lift the gas out of the gravitational well. So what I've plotted here on the figure here on top is on the horizontal axis is the radial coordinate away from the star. And on the vertical axis, you can see the velocity field. And in the background, in the blue shade, I've colored how much opacity is available at every radial coordinate for those typical densities and temperatures that you encounter there. So we see that close to the star, we have sufficient opacity to start and accelerating the gas. And this is due to, well, the iron opacity peak, which is close to the stellar surface for Wolf-Rayet stars. But so your gas velocity, which is the black line, will be able to rise, and so the gas can accelerate up to a certain point at around 2 stellar radii, where there is suddenly no more static opal opacity left to keep the gas, or to accelerate the gas more. So your gas will start to decelerate, and it will be attracted, gravitationally attracted back to the surface of the star. And after a certain radius, your gas will have decelerated and start to fall back onto the stellar surface. So what this means is basically that only opacities are not sufficient to push all of your gas away from the stellar surface. So we need an additional force source or an additional opacity source. And this is delivered to us by using line opacities. So line opacities are also the driving force between O star winds and B star winds, and they are typically described there by this CAK type of formalism. So what line force opacities mean is that you take into account the Doppler shifting of the line. So when you have a gas particle that gas particle that can absorb light very efficiently at a given frequency at an absorption line. If a gas particle absorbs light and get accelerated, it will have a higher velocity, and thus the absorption line will Doppler shift out of its own shadow. So the further that you are in the wind, the more that your absorption line is Doppler shifted, and thus you can, at every radial point, you can absorb more unattenuated light from the stellar surface. And the combination of these two opacities, so the CIK opacity or the line driving opacity is very efficient at low densities. So that can be seen here in the figure on top. Now your wind can be started or can be driven close to the star again by these static opal opacities which are very efficient at high densities. And then your wind will accelerate, and then when the opal opacities are not sufficient anymore, it will decelerate a bit. But then suddenly at around 3 stellar radii, your CIK or your line driving opacities become very efficient again. And this will re-accelerate your gas and drive it all the way to infinity. And this is basically what gives these velocity profiles, this typical two-bumped, this two-bumped figure or this two-bumped shape. So the combination of these two opacities is what we call the hybrid opacity model, and it has been described and found out about, cooked up by Luca, and is described in the paper that he published this year as well. So the first thing that we can do then with our FLD solver is try and recreate one of these hybrid opacity models. And we've done this. So in the plot here, in the red line, you can see the results from the FLD solver. So this radiation hydro method that I described earlier, and where we compare it to the original steady state models that have been computed by Luca. So the main difference here is the way that we do radiation treatment, and that this is readily expandable to multi-D setup in a time-dependent manner. So yeah, we can go now to our first 2D models. So the equations that I've showed earlier are solved in a finite volume type of way. That means that we take a numerical mesh, and in each mesh point locally, we solve those equations. Yeah, so I take a numerical box that is 5 stellar radii across and half stellar radii wide, and I paste it to the hydrostatic core of the star, which is here on the left of your screen. And then to make it computationally a bit cheaper, we put a lot of mesh refinement near the bottom of the simulation box. Typically in these wind simulations, it's very important to have a high resolution close to the star where your wind gets accelerated for the first time. And then further out in the wind, it's less important to have this high resolution, so we can do with a little less cells, and that will make the entire computation a lot cheaper. Okay, and then we impose boundary conditions at the bottom of the star, or at the bottom of the wind, close to the stellar surface. So that means that we keep a fixed density and a fixed luminosity or radiation flux that flows into the simulation box. But we let the gas energy float or self-adjust so that we can self-consistently calculate a core temperature. And the same thing we do with the momentum, so that we can self-consistently calculate the mass loss rate. And then on the side, we use periodic boundary conditions. So that means if your gas leaves the grid in one lateral direction, it will just pop up again in the other lateral direction. And then we impose initial conditions that have been inspired by our 1D simulations. And we then solve the RHD equations on that grid. And we do this then together with this hybrid opacity formalism that I've talked about earlier. And then we can just evolve the gas and radiation state, and we can see what comes out. There's one more note that I want to make here. Of course, stars are round, but solving these equations is easier on a Cartesian grid. So what we certainly have to do is account for the spherical fluxes, right? So what I mean by that, if you have gas or radiation flowing radially away from a source in a spherical set, if it's radially away, the flux per unit area of the gas or radiation will diminish as 1 over r squared. And this is not the case in a Cartesian box, so we'll have to sort of enforce that and correct for that in our simulations. Furthermore, sometimes I will, when I show my results later on, I will sometimes show this spherical pie slice type of plots, and sometimes these Cartesian boxes on the right, but they are the same simulation, so don't get confused by that.
Well, yeah.
So okay, let's get to the results. I will show you a video soon after this slide, where we actually use this model to model 10 solar mass star with a 1 solar radius and 10 to the 5 solar luminosities. And I will show you 3 panels, the same that you can see here. So on top panel, I plot the logarithm of the gas density. In the middle panel, I plot the radial velocity, where I set the color bar in such a way that yellow and red gas is flowing out, but when the gas is indicated blue, that means that there's actually gas falling back onto the star due to turbulence and all this structure formation. And then in the last panel, the third panel, the lateral velocity is shown. Okay, and then a note on the time frame. So one frame in the video is about 5 minutes in the star's lifetime, and the full movie will span about 5 hours of the star's lifetime. So here we go. Okay, so the takeaway message here is that there's a lot going on. There's a lot of dynamics, a lot of gas moving up and down. And if you look at the density, there's also a lot of structure formation. You have clumps, and it's not spherically symmetric at all. And this is structure that will, of course, all affect the transport of radiation through this medium, and thus also affect the formation of spectral lines in the wind. Yeah. So let's try and have a look at the density now when you collapse it to a 1D setting. So what I plot here is as function of radial coordinates. I plot the density of all the finite volume cells that we have for the last snapshot. And I compare this to the red line, which is the density as function of radius for a 1D model. Yeah? So first thing that you notice is that the 1D model is contained within our 2D model, the scatter plot. But another thing that you can see is that at any given radius, there's a huge spread on density, and the spread is at least 3 orders of magnitude every radial point. So again, this will affect the transport of radiation enormously as compared to just a uniform 1D model. And the same if we look at the radial velocity profile. So here I plotted all the radial velocity profile for every lateral cell, the radial velocity as function of radius. And again, overplotted here the 1D profile. And again, you see that when you compare the 1D profile to the 2D profile, in the 1D profile, you have a lot of heavier gas, which is indicated by the color map. So the overdensities are plotted in yellow, and the lighter gas is plotted in blue. So you see when you compare the 1D to the 2D profile, that in the 2D profile, there's a lot of more heavy gas that is moving slower as compared to the 1D wind, but also that there's a lot of very light or undense, very sparse gas that is moving a lot faster than in the 1D profile. So this gas will also have a higher V infinity, which is an important parameter that we measure from spectral. And yeah, you see that the gas, so that the very undense gas can be up to 4 times faster than in the 1D setting, or even more. Okay. So, and again, yeah, that will have an effect on the radiative transfer. So one immediate result that we can get from this simulation is the clumping factor. And the clumping factor is a statistical parameter that tells us how smooth or how clumped our wind is. So what I've plotted here in the color map on top is again the relative density to highlight the clumps or the structured material. And we find that for this particular 10 solar masses, 1 solar radii model, we find a clumping factor of about somewhere between around 10. And this is a result that we can immediately incorporate back into 1D spectral synthesis code, such as fast wind or CMF-Gen or power. And then another nice result that we get from these 2D simulations is that we can, as a function of time, track the mass loss rate, and there's also the variation in the mass loss rate. So here you see the total mass flux through the outer boundary of the simulation plotted as a function of time. And we compare this to the mass loss that we get from a 1D steady state model in the black dotted line. And we see that actually the mass loss rates are very, very similar. So that's a nice confirmation of our model. One note though here, so we see a lot of variation in the mass loss rate for the 2D profile. And the magnitude of this variation is, of course, not representative for the full star. We only probe with our 2D model a small part of the stellar surface or of the solid angle. So this is the order of magnitude high oscillations are of course not to be understood as the actual mass loss rate fluctuations. And then the final result that I will show you from our 2D winds is related again to this core radius problem that I talked about earlier. So in our 2D models, we can now integrate over optical depth to actually compute the location of the photosphere, where we say that the Rosland mean optical depth should be equal to 2/3. So, and we find that for our 2D models, this is typically at around 4 times the stellar radius outside, so at 4 stellar radii. And the temperature at 4 stellar radii is a lot lower than the temperature at the hydrostatic core. So this means that when we observe light from a star, or if we were to observe light coming from this star, the temperature that we would actually see would come from the photosphere and not from the hydrostatic core. So, and if we then, so if we try to assess the temperature coming from observations, we can now understand that this does not come from the actual hydrostatic core. Okay, now we will go to our 3D models. So yeah, that was it for 2D models. Let's go to the 3D models. The nice thing about MPI AMR, like the code that we use, is that it's very easy to design a problem in 1D and then expand it to 2D and 3D. So one might think, why do we need 3D models? Well, all of these instabilities that we saw in these 2D models are very reminiscent of the Rayleigh-Taylor instabilities that we encounter in gas flows sometimes. So when we know that Rayleigh-Taylor instabilities are different in 2D than in 3D, or different in 3D than in 2D. And furthermore, if we run these models in 3D, we can actually model the full structure, the full 3D structure of the clump, and answer questions such as, are the clump blob-shaped or pancake-shaped, or what 3D shape they have. So 3D models are just more physically correct, but computationally they are very expensive. So a couple of orders of magnitude more computation time or more core time than 2D models. So yeah, again, I will show you a small video of one of our 3D simulations. So here we have exactly the same setup, but now in 3D. So we model a 10 solar mass star with a 1 solar radius hydrostatic core and 10 to the 5 solar luminosities at the bottom. And the radial extent of the domain is again 5 solar radii and half a solar radii wide in both lateral directions. And what I plot here are the, again, our surface contours of the relative density. So the yellow blobs that you see will have 5 times the relative density, or will have a 5 times higher density as compared to the average density at that particular radius. So I will play another movie. And yeah, the nice thing about these models is that we can now actually have a look at the full 3D shapes of these clumps, right? So here we see the same simulation displayed in a different way, where we have a volume render of the density on the left-hand side, and we look at the radial velocity at certain lateral slices on the right-hand side. So now that we have the full density and velocity structure of these winds, we can use them in a post-processing way and actually perform full radiative transfer on them, so that we can compute frequency-dependent intensities and fluxes, and also synthetic observations. So that's exactly what I've been doing with one of our group members, Leuven. And what you see here is the specific intensities that we retrieve from doing short characteristics radiative transfer. And we express the specific intensity here as a radiation temperature. On the left-hand side for a continuum frequency, and on the right-hand side for a frequency in a spectral line. And so what this means is that if you were able to travel to a Wolf Rayet star and actually be close enough to resolve the Wolf Rayet star spatially, this is exactly what you would see on the left-hand side if you used a band filter that passes through continuum light, and on the right-hand side if you would look at a star with a filter that passes through light at a frequency of a absorption line. So you can see, of course, that there's a lot of structure going on here, and from these figures you can also see the right-hand figure has a bigger surface area and a higher total intensity than the left-hand figure. So this is the reason that lines are in emission for these stars. And this is in stark contrast, or like the structure that you see here, and everything that's going on is in contrast with the 1D, the previous 1D models, which are just spherically symmetric. So when we do observations, we actually integrate over the full intensity here, and that provides us with a stellar line, or with the flux at a given frequency. So if we do this for multiple frequencies, we can actually compute synthetic spectral lines. And so that's what we've done here. So here we are showing the first synthetic spectral lines that we've computed for our 3D models. So those are in blue, and we compare these to a synthetic spectral line that we've computed using a 1D spherically symmetric beta law velocity, where we use the same stellar parameters, the same mass loss rate, and the same asymptotic velocity. So what you can see from this is that there's a huge difference in using either a 1D beta law or a 3D hydrostructure when computing your spectral lines. So the other way around, if you would either use a 1D or a 3D structure when fitting to actual observed spectra, this would have an effect on the stellar parameters that you infer from your spectral fitting. And as a matter of fact, 3D models are in this case just more correct than 1D models. So for example, if we know that all other stellar parameters are correct and we are just fitting for a massless rate, for example, if you would use a 1D model, you would underestimate the mass loss rate as when compared to this 3D model, because you see that the equivalent width of the 1D model of the red line is just bigger. The surface under the red line is bigger than the surface under the blue line. And this is true for the mass loss rate, but similar things are true for all other stellar parameters, such as the abundances, radii, log G, and so forth. So these are sort of our results so far. So what's next? from here, we're going in two directions. So first of all, we want to have a more quantitative look at how these 3D models affect our spectral synthesis of observed spectra. So we'll do this for actual lines and then compare these two observations. And then the other line forward is actually expanding these models. So I talked today about Wolf Rayet stars, but there's no reason that we should just stay to Wolf Rayet stars. These exact same techniques, these models can be expanded quite straightforwardly, also to red supergiants, luminous blue variables, and yellow supergiants. And this is, of course, interesting to understand the full way from a main sequence stars, from a main sequence star all the way to a supernova. So that's it for today. I'll leave you with a couple of conclusions. So we've created the first multi-D models for Wolf Rayet atmospheres and outflows. And these have allowed us to study the atmosphere and wind structure and the clumping in Wolf Rayet outflows. So we've shown that these multi-D models are actually necessary for doing accurate spectral fitting. And in the future, yeah, at least for Wolf Rayet star. And in the future, we would like to look a bit more at the spectral synthesis with these 3D models, but also expand our models to other evolutionary stages, which are important in understanding massive stars and the remnants that they leave behind. Thank you. That was it.
Thank you very much, Nico. It's not an easy topic, and you managed to explain it quite well. So thank you. Are there any questions? If so, please mention it in the chat, and I will call out your name. The first question is from Dominic.
Hi, Nico. That was a really, really good talk. You should be proud of that. And some really fantastic results as well, actually. Good results mean lots of questions from me. You have made me very excited with your 3D models. So you might remember a couple of weeks ago, I was asking you about getting us potentially some time series, particularly in temperature, maybe velocity as well for your stars. How have you approached that, if you have thought about it since then?
Yeah, I have thought about it a lot, and we've not actually run the simulations yet, or the longer time-based simulations. First of all, because we wanted to sort of fine-tune our models a little more. And when I showed my models earlier in the GetKit, those were the very first fresh from the press results. So now we first of all have a lot more certainty of our models. And second of all, I've been thinking about it, and I'm still not convinced that we will actually find any long time scale variance, just because there's no physics in our model that works on this time scale, right? So I agree that if we add some sort of external physics or rotation or something, that might include some or induce some longer scale variations. But I'm not sure if we should expect it from these models. However, I will certainly try and run a longer model, because we can just do it now right off the bat.
It would be super useful. And the same thing was told 10 years ago of why do we need 3D? I'm happy with 1D and 2D. And then it's only when you run it that you find out that it gives you different results, which you've proven today. So I would encourage you to try. Yeah. My second sort of comment, it's more of a request. Do you really need to go to these late stages? It would be so much more fun for you to do some O-stars, maybe at the terminal age main sequence as well, to try and put some clarifying context on the people in the high mass community that think that winds and surface convection can explain everything in nature.
So the nice thing about our models is that they are very very general, right? So I don't think that there is a problem with doing O-stars as well. Certainly worth looking at. I think.
That sounds like a political answer, but that's okay. I can work with that. Thanks very much, Nico. This is really good.
Thank you.
Okay, thanks, Dom. Then the next question is for Tomer.
Yes, hi. I joined Dom in saying these are very, very remarkable results. I also really like them. It's also the first time I see the 3D results. So really nice. I have, to formulate this into a question, I would say, so right now, the status is that for calculating 1D non-LTE models, you know, power, SMFGen, all these codes, you typically need something of the order of hours, if not even a day, depending on how complicated the model is. So where is the trade-off here, that you're going to 3D and you can actually calculate spectral lines? You're not solving the full non-LTE problem. So can you comment on this maybe? Whether there's a trade-off here in accuracy?
So yeah, first of all, if we are talking about timescales, indeed, that the 3D runs that to compute the structure takes a couple of days on the supercomputer, right? So that's not comparable to the very quick spectral synthesis that you do with 1D models. And second of all, so no, when we do the dynamics, we don't do any fancy NLTE stuff, but this can happen in post-processing. Again, so when we do short characteristic solving, we can do that using Levin's code, I assume. But I have no idea, honestly, on how long that would take.
Would just be because non-LTE usually means like accounting for all the different population numbers and how they interact with one another. So it sounds like it won't necessarily be feasible, and I'm just wondering, when moving from non-LTE 1D to full 3D, but with some assumptions on the non-LTE, what are we compromising? Maybe it's a difficult question for now, but
yeah. No, I get the question, and I get the comment, but I'm not sure how to.
Maybe if I am allowed to jump in here, Levin speaking, right? Honestly, Thomas, I don't know either, right? I mean, it's simply, you cannot judge it if you don't have the a full 3D and LTE as a comparison, how accurate the assumptions, for instance, only calculating a single line, or assuming LTE, sometimes we can do this as well, right? We cannot judge it if we don't have a comparison full 3D and LTE model.
Yeah. Sounds correct. Okay, anyhow, great, absolutely fantastic work. Thank you.
Okay, then the next question is for Karen.
Hey, Nico, really nice talk. I have sort of two questions. One on the spectrum that you showed by comparing 1D and 3D. Could you, I'm not sure I quite understood why the intensity of the line was lower. Is it just because you have more optically dense clumps in front of the material?
So yeah, I think for sure that what we call it, the porosity effect is very important for this, right? Or where your material is clumped together. This, and also so the 1D model is here computed from a beta law, and if you compare the beta law, for example, to one of these 1D hybrid opacity models, you already see also that the 1D hybrid opacity model is more, well, just is expanded differently than the 1D beta law. So already that effect can change the equivalent width here of your lines. That's not per se, I don't think that's per se a 3D versus 1D effect alone, but also, yeah, also the expansion of the width.
Okay, thanks. And my second question was more to the 3D simulation that you showed with clumps. I believe that if you run it for a little longer, like, yes, exactly this one. So if you run it for a little longer, you see that there is some sort of periodicity in which the clumps are formed and the way clumps propagate, and also the amount of clumps, if I'm allowed to say that. But yeah, I think this is really interesting because we do observe it on the tops of some spectral lines for Wolf-Rayet stars. So if we could get, and we have data with Hermes that is also high quality, that probes these short periods.
Yeah.
So if at some point you're able to get synthetic spectra out of these, it would be interesting to compare.
Yeah, that sounds very interesting. And yeah, we already have these model atmospheres now. So the spectral line that I showed at the end is indeed for just one snapshot, but we can with this method easily look at the time variability as well. That's true.
Yeah, so I mean, I just realized I didn't ask my second question. And that was, would it be possible if you had this sort of a block to compute a spectral line? But I guess you answered it.
Exactly. Yeah.
Yeah.
That's
Thanks a
very
lot. Yeah.
welcome. Thank you.
Okay, thank you, Karen. Are there any other questions? If not, then I would like to thank Nico again. Thank you very much for your interesting seminar.
Thank you.
Then we will see each other next week with Vincent van Erlen. See you. Bye.